Hello everyone and welcome back to our series about teaching maths in the FET phase. First, let's start by taking a look at our video dealing with similar triangles. The English language describes the word similar as having the same or some of the same characteristics. In geometry, the description is far more precise and describes two shapes which look identical except that the one is either larger or smaller. The mathematical definition for similar triangles is that they must have corresponding angles that are equal, while the lengths of the corresponding sides must be in proportion. They therefore have the same shape but not the same size. In today's lesson at Alexandra High, the maths teacher Caroline Nglanga is teaching her learners about similar triangles.
Here we're going to look at what similar triangles are. What are the properties of similar triangles?
The outcomes for the learners are to explore real-life properties of similarity using models, investigate and test similarity in triangles, practice naming triangles in order of similarity, and to write proportionality equations by using the order of similarity, and demonstrate an understanding of similar figures by utilizing the properties of these figures to solve real-life problems.
I wanted them to be able to define similarity and to be able to prove if they say these triangles are similar, what is their reasons? What are the properties of similar triangles?
The teacher begins her lesson with a trick that can be explained by using similar triangles. This immediately engages her learners in a real-life situation. She puts a mirror on the floor facing up and asks the student to stand a meter away from it. She then positions herself so that she can just see the top of the student's head when she looks in the mirror. With a quick calculation, she reports the student's height.
So Kolani is about 1,32.
The teacher then explains to the learners that she did the magic trick by using similar triangles.
So in a nutshell, we have calculated the length of Kolani using similar triangles.
In this activity, learners are presented with a worksheet containing diagrams of 4 beetles.
Then you're going to say which ones are similar and you tell me why.
At first, many of the learners base their decisions on the English definition of the word similar.
Fat. Skinny.
Also fat, but then all of them have 6 legs, feelers, or if you can say feelers or antennas.
The learners are reminded about what similarity means.
But remember, one property is that similar is the same shape but different size. Other property is proportionality. Have you tried using measurements?
This activity involves learners making decisions on how to determine when shapes are similar in a geometrical sense.
Similar to D and B is similar to C because of the spaces here in between the wings or the legs. That's why we say that, and the length, the equal.
The teacher moves around the groups listening to comments. Some learners guess by just looking at the figures.
A and B.
Why?
Because you see, they are designed the same. They have the same shape, but the sizes are not the same. This one is big, this one is small.
Other learners measure the shapes for equal ratios.
Well, we first measured the breadth of the bag A, which gave us 40 millimeters, and the length gave us 39. That is a ratio of 40 over 39, and we acquired an answer of 1,02.
In the same way a ratio was determined by measuring the length and breadth of bag B, the ratio of A and B were the same.
Bag A and bag B are similar because they have the same ratio in their width or breadth and their length.
With similar objects or similar triangles, we are talking about the same shape but different size and the same proportion of corresponding sides.
In this activity, learners are required to draw 2 pairs of triangles that will demonstrate the principles of similarity.
The first one is for angles. You are measuring angles. You'll be using protractors there. And then the second one, you'll be using measurements, measuring the sides of the triangles.
For learners to accurately complete this activity, they will use their compasses, protractors and rulers. Accurate measurement is always difficult, and reminding learners on how to execute sketches comes in handy.
And they were struggling to draw the angles, the equal angles, because they had to measure. They didn't know how to draw the straight line first and then, or the circle first, to get the 90 degrees right and then measure from there.
A successful outcome will be if the learner can illustrate an understanding of the two test cases.
These triangles are similar because they have the same proportion. If we divide 10 by 8, we'll get 1,25. And if we divide 5 by 4, we'll also get 1,25. So this shows that they have the same ratios. Therefore, if they have the same ratios, it means that they are similar.
I started by drawing a triangle, and then I drew this line, ET, and then I drew it in such a way that it became parallel to AB. Therefore, I measured this angle here, A, and then D. And then they were similar. They are equal, and they are corresponding angles because we have parallel lines. And then again I measure this angle B and then E, and then they are equal. And then this one was common. In a way, it's an angle from two triangles. Therefore, you can say that CPE is similar to ABC.
The learners have shown the criteria for similar triangles, demonstrating proportional sides and equal angles.
Therefore, triangles are similar if the sides of triangles are
Proportional.
or when the corresponding angles are
Equal.
If you have to prove similar triangles, you don't have to prove both cases. You either prove the angles are equal or the sides are proportional, okay? So here you have a triangle ABC and triangle DEC. You are given that.
We are given that angle DEC is equal to angle ABC. Learners are required to mark off the other equal angles.
And then after that, you write down two similar triangles in order of similarity and explain why they are similar.
Learners often struggle when testing for similarity between triangles that are within triangles. In this case, the learner draws the two triangles separately.
Triangle ABC is similar to triangle DEC.
Okay, why?
Because C is common and angle E is equal to angle B is given, and angle D is equal to angle A because the angles of a triangle are equal and they add up to 180 degrees.
Write as many possible proportions comparing the sides of the two triangles.
Learners find it difficult to move between the triangles in the diagrams and writing down the equivalent proportions. They do not know if they must make each ratio up of the values of the one triangle or combine the triangles. For example, triangle 1 side A over triangle 2 side A is equal to triangle 1 side B over triangle 2 side B, or triangle 1 side A over triangle 1 side B is equal to triangle 2 side A over triangle 2 side B. The teacher introduces a technique to aid the learners.
If you take proportional side AB over proportional side DE, then BC, EC, and then, so that's what we call a Batman cave.
Using the Batman method gives the learners a comfort zone in writing down their proportions.
So we have two triangles at the bottom there, ABC and DEF. So those triangles, you must prove that they are similar.
The teacher will remind learners of the naming of triangles according to similar angles.
We say triangle ABC is similar to triangle DEF because the sides are proportional, and the ratios are the same. AB over DE, we divided the 6 and 3, and we got 2. Then we did BC over EF, BC over EF, which is BC is 10, EF is 5. We divided, and it's equals to 2. And this one, AC over DF, which is 8 AC, and DF is 4. We divided and got 2. That's why we say the ratios are the same, and the sides are proportional.
So we're going back to the magic trick. So we need to do...
Now that learners are comfortable with the concepts of similar triangles, the teacher will explain how the height of the learner was determined. She begins by representing the practical scenario on the board.
We have my height, the distance from the mirror. There's the distance from the mirror for Golan. How can we get the X? Okay, we say the mirror is here, okay? It's there. So we have 90 degrees on both triangles, triangle DEC and triangle ABC. And then there's a mirror image there. Let's try to do that. At least it's straight. So it means this angle is equal to that angle. So we have two angles equal, and we can say the two triangles are similar. Therefore, this one will be equal to that one. Angles of a triangle equal to 180 degrees. How can we get the X?
AB over BC
is
equals to DE over CE
or EC. So we can use the numbers, ne? The numbers we have. AB is 1,72. BC 1,3 equals to DE x CE 1 meter.
The teacher and learners substitute and come to an answer.
1.32 meters.
1,32 meters. So Kolani is 1,32 meters.
As a final activity, the teacher gets two learners to do the same activity. They begin by measuring one another.
1.8 meters.
The mirror is positioned and measuring takes place.
The distance is 1.2 meters.
Learners fill the measurements on a worksheet, and after working out proportional ratios, the other learner's height is determined to be 1.5 meters.
Learners are able to work together as in groups. They are able to use their pre-knowledge. So it's the duty of the teacher to be creative and to bring in their pre-knowledge into class.
Learners test their results.
Prove that Christina is 1.5 meters tall.
Now that we've seen our video, it's time for us to welcome our guests. We've got Smangali Sotwala, who's an independent maths consultant, Mara Hockman from the Wits School of Mathematics, and we've got Catherine Hunter, who's also an independent maths consultant. First question, let me start with you, Mara. What do you think of the way the lesson was structured, especially around the so-called magic trick with the mirror?
I thought it was a lovely lesson. The magic trick with the mirror, reminding us of similar ideas of how do we measure tall buildings, how do we measure the height of a pyramid. But what I really liked was that she started with the lesson and she brought this magic out, and she ended with it again. So she brought the cycle to conclusion. She did the trick, which was a trick at that point, and she then brought them into the circle and then allowed them to complete it themselves. I thought it was excellent. The whole cycle had been completed. just on a point of the idea of similarity, the idea of scaling is paramount to the way we live our lives in our Euclidean life. Without the ability to scale, without the ability to have similar triangles, we wouldn't be able to function in this world. We wouldn't be able to build a building or construct a road or to do very little. So the idea of similar triangles is really important to our daily lives, and for the students to get a handle on the idea of scaling is paramount.
Okay. Add to that?
Yeah. I think I also like the activity, like Maria said, that she started with the trick and then did some things and then came back to the trick, and the children could actually see that this wasn't a trick. She actually used some mathematical concept to actually solve the problem. Mine would just be to say, I wonder whether the children themselves can actually find other similar problems that they could actually solve with the mirror and so on in real life.
Catherine?
I thought an interesting extension to the activity, which definitely had a very clear beginning, middle and end. So perhaps for a future lesson could have been to take children out into the playground, which in any case is an unusual learning environment for them and adds variety to their learning experience, and to ask them to find the height of a tree or some familiar object to them that is very high that would be very difficult to verify the height of, in fact. But once they've trusted that you can use similar triangles to find heights, and of course you could include the shadow of a tree and where does that fit in, to get them to go out and to use it in their lives practically.
Smiley, so what do you think are the main difficulties that learners have with similar triangles, and how should teachers overcome those problems?
In most cases, you find that learners do not actually understand triangles themselves, and as a result, you find that they don't even know that the orientation of triangles. If you turn a triangle and you put it in another way, then they don't see that as the same triangle and so on. So you find that when children are battling with that, and you move on to similar triangles, then that really throws them out. The other thing is when teachers actually relate similarity to congruency, and that creates a lot of problems, because then a congruent triangle is, a similar triangle or similar triangles are not necessarily congruent, but congruent triangles are the ones that are similar.
Okay. Meira?
Yes, I think the idea of similarity and congruency does get mixed up. Perhaps it's unfortunate that the signs that we use to display congruency and the signs that we use to display similarity are so similar, and if one can't remember which is the horizontal and which is the vertical, everything goes to pieces. I do think that the schooling concentrates a lot on congruency, and perhaps there's too little attention paid to similarity, which is by far a much more exciting domain for me. And in terms of the application of similarity to the world, you blow up a balloon, you project a light. All these ideas are of similarity and not of congruency. And it's very exciting. The applications of similarity are all around us. I mean, you have to choose which you're going to use because there's so much you can do. But in terms of lesson plan, it's the conditions of similarity which cannot be used as conditions for congruency, and I think that's the big problem. Students cannot use corresponding angles are equal as a condition for congruency, and that's where technically they get into trouble. So that's what I would highlight in a lesson. Once the lesson has gone through and you're saying, how does congruency match up to similarity, one has to pinpoint the actual conditions as being very different.
Okay. Catherine?
Arising out of both of the two previous points, I think it's quite important. First of all, Smangaliso mentioned the idea of having triangles put in different orientations and emphasizing the fact that, of course, triangles can still be similar even though they're twisted around and pointing in different directions and so on. And arising from that, the fact that learners need to understand what is a corresponding angle. The teacher did teach it, and I think fairly well, but I think that he would find that, she would find that in fact learners would struggle to be able to correctly name and refer to angles and to triangles, and highlighting the fact that maybe they don't recognize what the corresponding angles are and the corresponding sides and the relevance that has in the idea of proving similarity and congruency as well, of course. So I think that would certainly have to be emphasized, even though it is addressed to a certain extent in lower levels.
Okay, and going back to the teacher, how effectively do you think she managed the class?
I thought she was. It was quite well done. It was certainly based on experimentation, bringing particular learners out. It was difficult to see how, in fact, she would get the learners to work together in teams. And I think that it's quite important. That's quite a central part to the extent to which a learner will actually grasp the necessary meaning. Yes, the teacher does have to make sure that each and every learner, including the passive and the quiet ones who choose to sit at the back and so on, the teacher has to check that they are grasping as fully as anybody else what the learners are meant to leave that classroom with. She certainly needs to emphasize that. But one thing she could do is to make sure that strong learners and weak learners sit together, and perhaps not let learners choose to who they want to sit with in completing their worksheets. They look like very interesting worksheets, but to allow learners to talk, to communicate with each other, and to have, as I say, strong and weak working together in groups of maybe no more than 3, ideally, so that they are all very forced to participate fully, take responsibility for learning and so on. But I certainly thought she involved the learners, and she had a wide variety of activities there as well, bringing learners out to the front to do that so-called magic trick, and as well as doing worksheets, and there was a buzz in the classroom. I thought it was great.
Any other issues you'd like to raise?
What I liked again about the teacher is that similarity, once one's established, and as Catherine said, it's quite hard to establish which triangle, how the triangle is in proportion with another. But once that proportion has been established, the little algorithm that she showed them of how to pick up the sides, that Batman exercise, very valuable, because once we've got the triangles in proportion, in order to get a handle on it, it's quite confusing. You know, you can almost detach yourself from the triangles when you've got that little algorithm. So that was a very important insertion that she made. However, to emphasize again, the algorithm should only come once the triangles have been seen to be in proportion, the students are convinced they're in proportion, then the algorithm can step in, and then the conclusions about which side is proportional to which side can come into play. So I liked that in her lesson. I liked the fact that she gave the algorithm to the students, but well into the lesson. It wasn't like up front, it came afterwards.
Okay, well, that's how we come to the end of this session. Thank you very much for joining us, I guess. Smangaliso, Mera, and Catherine. That's how we come to the end of it. Thank you for joining us. Goodbye. We'll be with you again next time.